The processing in the FK domain, we simply call it FK filtering. So FK filters, we transform time-space domain events into the FK domain so that we can separate the different events based on the dipping angle, right? So this is a cost of dipping. Dip is how many seconds per trace, okay, or per data X. If we do the filtering, the simplest way is we multiply 1 to the part we want to keep, multiply 0 to the part we want to remove. Because the Gibbs phenomena, which we in the boundary, we should somehow use a tapering gradually from 1 to 0. Okay, most likely you just use the cosine taps. Right? If the spectrum is a power spectrum, we use a cosine squared. I personally experienced that. I use cosine squared, but it's the same thing because amplitude multiplied by cosine, power spectrum multiplied by cosine squared. Right? The taper have a very good behavior. The taper almost similar, almost the same as a Gaussian function. Gaussian function have a special properties we explore in the signal processing many, everywhere almost. One of the attractive properties of a Gaussian function is its transform is also in Gaussian. It's also in Gaussian, gradually decayed, right? So cosine square is similar to that. And the filter, we usually use a so-called pi slice, just like we have a pie. We just cut off a slice for different person, right? That's called pi slice. Or more complicated, more sophisticated, we use a polygon, just cut everywhere. Use a polygon. So that's the filter. This cartoon here just shows how to do the FK filter. That's a two-dimensional spectrum. Vertical axis here is from 0 to 100 Hertz, which is frequency, temporal frequency. Horizontal axis is from a negative next wave number to 0 to the positive next wave number. Okay, so you have something here in this color we call the pass tone. That means we multiply every sample here by 1, which means we do not change, right? But outside we try to reject, we just multiply by 0 everywhere. In this case, if we reject this, we try to get rid of this energy here. That's energy actually elicit. When this is to the edge here, and then wrap around to another side to here. You can see that? That's energy, right? So if we know your data actually the elicit, the data you got from the field is elicit data. You try to get rid of this elicit frequency, elicit wave number. What do? You do this filter. You get rid of this. Meanwhile, you get rid of the elicit part, right? So that's, you see the shape here, just like a pie. So this is called a pi slice filter. That's straightforward. If we're much more sophisticated, you try to keep this corner here. Keep this. You think this is the useful energy. You just do slightly sort of refine the job. You cut from here to here, right? That's called use a polygon. It's a polygon field to do that. Yeah. You get rid of this noise trend, but also elicit the noise trend here. But you maximally keep those energy of the field, right? That's passed on, and that's simple. But in the time domain, it's not so simple. Field in the FK domain is simple, but in the time-space domain, that becomes two-dimensional convolution. So we prefer work on this field, in this area. That's a shortgetter from a field. In this case, you have energy from here to here. You also have you can see the curved energy here. That's the refractions. This energy most likely from here, right? If horizontal energy will be vertical here, okay? But you also have something here, you can see. That's because of wraparound, cause some in the pre-processing, where this energy goes to. That's okay. If you taken this as negative, because there's they use access from here to here, depends on you how to define it, that X, right? If we keep this as negative, that way positive, you can see here. That's the one. Or if lower frequency energy is actually this one here. Okay, and this part actually is wraparound over here. If we want to get rid of this LSD, you need to cut off this bit at least, or you also need to cut off this, right? But also you can cut off this, so you can do the field on that. Just get that showed in the AGC. Now you can see what do you try to do? We try to keep this, get rid of the first arrival, also get rid of LSD part. Right? LSD part here, LSD part here. But maybe you can also do something here, but okay, you do not do that now. So you have this. And the resulting is this part of LSD energy. If we go back to the previous one, you can see the channel here, which is a lower frequency. It's here. It's gone now. And also very strong arrivals here. It was appear here, now it's also gone. That's the FK field. Let's compare the data before and after FK field. That's before, this after. I already point out here, this the dipping event disappear after field. And also this strong linear events actually becomes, this linear becomes attenuated almost, right? And then now you can see the reflections actually stronger relative, right? Because the strong linear events there. So now, because strong events removed, so you can see reflections both up after AGC. Let's display both after the AGC, right? Okay. Some events here, very low frequency after field is gone. Yeah. That was FK field application. Now let's see examples on the multiple removal. We saw this diagram before. We have 3 CMP getters named red, green, blue, 3 CMP getters. We have water bottom reflection and some reflections, but this looks like a multiple, this reflection, right? After NMO and the stack, NMO, we have this layer flattened. However, the multiples is not flattened, right? So after stack, the stacking will cancel part of multiples, but the near offset tracer, I mean next to 0, right? Near offset tracers, they have no much time difference. So after stack, you still have residual. You can see for this color, at this gather here, blue for here, you can see the events here, and right. So this one start from here to here, right? That's the one. And this is another multiples. You can see still have a multiple residual. This is the result of NMO stacking. We gather some multiples, but not completely. Mechanism of multiple generation, time, and this receiver station, which is offset or X. But this water, if it's a constant velocity from source to the receivers, you have a straight line. So this is called a direct wave. For the water layer reflections, here you have events look like this. The curve depends on the offset because velocity is constant. Right? This curve is absolutely hyperbolic because the velocity is constant in the water layer. It's accurately represented by hyperbolic equation. We have a multiple. You were propagating through water twice, bouncing twice, down, up, twice. Here, down, up, twice. You have just like you have another reflection here. Looks like, okay, apparently looks like you have another reflection, just like a primary, but the velocity is water layer velocity, same as water layer. So you have here, right? In the near offset, in the zero offset, this actually time just doubled. Okay, but if we have a true reflection here, your curve, because for the primary here, the velocity from the stacking velocity is higher than the water layer stacking velocity. Water layer stacking velocity is equal to water layer velocity. Right? It's higher, so the curvature will somehow cross over the multiples. See? These two primaries and the multiples have different curvature. Right? If I have a peak leg multiple, which means that you are adding another peak leg here. Peak leg multiple, you have this is the primary, the peak leg multiple, almost parallel to that, and the time delay is equal to the water layer time delay. You see that? This is increased by V here. Okay. So now you can see in your CMP data, you have a primary with water layer, water bottom, and the water layer multiples, and they have a primary for reflections and the water layer peak leg multiples. Yeah. Because the curvature different, so really means because the velocity different. Remember, FK transform, in the FK transform domain, any dipping events in the time frequency domain becomes another dipping events in the FK domain, right? And the dip is the inverse of velocity. Here we have for seismic data, we have velocity difference. That means we have dip difference in your FK. So that means we can explore the difference in terms of dipping angle to separate them. That's the mechanism, okay? So we can explore velocity differences between the primary and the multiples, right? And how we do that, practically, we try to overcorrect the primary, which means instead of we correct the NMO, use NMO to correct the primary as a horizontal layer, flat event, but overcorrect. Use a higher overcorrect means with a lower velocity, right? We overcorrect that, and the multiple, so that the primary will have a negative dipping angle, and but the multiple is still undercorrected. Multiple always undercorrected, right? So that means you have a primary and the multiple after FK transform. They have they're both one in the negative K, one in the positive K. So you separate them into positive K, negative K, right? And then you apply FK field. You try to get it for either positive K or negative K. Keep it another part. After transform, because your NMO is not the true MO, as you use different velocity to the true velocity, NMO velocity, right? So you need to remove this NMO, go back to the original move out, and then you do the proper NMO. So this is FK demultiple procedure. I show you how to do that in this diagram. And normal NMO, what we do, we try to make this reflection events become flat, completely flat. This is what we try to do. But if we use a true NMO velocity, the multiples here in red, they are undercorrected because the velocity too high. Velocity higher than the multiple layer velocity, higher than the water layer velocity. So that's a normal NMO. But for FK demultiple, we overcorrect the priming. Instead of we make it a flat event, we just overcorrect, right? So that means you have a up dipping here, but the multiple still under corrected. After FK, they will be in positive and negative K domain, right? So the FK transform, primary in the one domain, in this case, just put the negative K and the multiples in the positive K, right? So now you can do the Fourier, you can do the filtering. You try to either get rid of multiple or get rid of primary and then subtract the multiple, subtract the primary, subtract the multiple from a primary, right? The same thing. Okay, just depends how convenient for you, because some minor slight tuning procedure, so you can do either way. But anyway, FK domain. It's just in this case we just simply reject the multiples. Right? Again, here is not simple cut 1 to 0. You need a tapering here, right? Otherwise, you have a Gibbs phenomenon. Demonstrate some examples. Right. Here, the raw data. You can see you have events look like this. Suppose it's our premise, right? And that's also a premise. But in between, you don't know it's primary or multiples, right? But how we do that? Normal NMO, we try to make this hyperbolic curve to be flat, right? Recall that after NMO, we have something wrong in the far offset. We call the stretching factor, if we recall that, right? Stretching factor. Stretching factor means the delta T after NMO over the delta T before NMO. T1 minus T2, okay? So this, the same waveform after NMO becomes stretched, right? In the length enlarged. So that means your frequency, actual frequency, gradually decrease. So actually has a drastic negative effect to your data, right? What we did for the NMO, we have two ways to do that. If we remember at least one method to get rid of the stretching factor, I think I introduced two ways to do that. Yes, the straight way, the brutal way, just mute out, right? Based on the straight line, which is set up the threshold of stretching factor. Yeah, if you recall that, I think a red line, but right, that's one way. If we cut off the larger wave number, that means we lost some information here, right? Okay, what's another way to do that? The muting also actually not only get rid of a stretching factor, but also get rid of the far offset that's not flat, right? Because for narrow offset it's fine, but for a longer offset, you never get flat. Use an NMO formula. what do we do? Can we improve that to get the flat even for the intermediate or for the large offset traces? We can do an MO get flattened. Right. Okay. Let me repeat. NMO formula is came from a simple model, which means we have a single constant velocity layer. The formula, the time move out, right? The time curve satisfies hyperbolic equation. You see that, right? So that's only two terms: T naught square plus another term, which is an MO correction. But in reality, we have a multi-layers subsurface model, multi-layered, right? And the only thing we can do tail expansion. We have a second order, fourth order, sixth order, because squared, right? So you have second order, fourth order, even orders, right? The difference between the tail expansion and the accurate hyperbolic equation is the tail expansion we truncate at second order. Yeah, we ignored fourth order, sixth order, and higher orders. Yeah. So the easy way to do that, we try to include more high orders, include fourth order and the sixth order, right? Okay. Even though you use a sixth order, still do not have an ideal, optimal NMO velocity, optimal NMO correction result. What do we do? I actually one stage I mentioned called optimized sixth order, which means we use an inversion method to instead of directly derive the coefficients for the second order, fourth order, and the sixth order, but we treat each of the coefficients as an unknown variable. We use an inversion method to do the optimization. Okay. So the second way is to try to increase the high order term. If we increase the high order term, this part, the stretching factor, will be much smaller. Right? For the near offset here, you do not need a mute, but even for the long offset, they actually have better flattening effects. Okay, that's the two way to do that. Right. Now, if you want to overcorrect this, overcorrection means you have a dead NMO correction larger. Right? As I said, hyperbolic curve have a left-hand side is a t square, right-hand side have a t naught square plus NMO correction term. NMO correction is the ratio of offset divided by a ratio of offset over the velocity, right? If you want to overcorrect, it means you want this term becomes larger. Really means you want the denominator become smaller, which means you try to reduce your NMO velocity. Yeah? Overcorrection, to achieve overcorrection, you just reduce your NMO velocity. In this case, I showed 90% of a true velocity, a true NMO velocity, okay? You can see this overcorrect, okay? And then, even overcorrect, you still have events in this way. Those are the multiples. These are the multiples here, okay? And then you do FK filter. FK filter means you do this time x two-dimensional data, just like a matrix. You have a column, you have a rows, right? So the two-dimensional Fourier transform becomes another matrix. You have a temporal frequency and spatial frequency. Right? And then you manipulate your data by multiply 1 or zeros, right? And then you do the inverse. Fourier transform and inverse transform are identical, only change your sign. So the calculation same, very efficient, and then end up with this result. So any trend in this way is completely removed, have been completely removed. You only have this trend, right? Because this one is not true NMO, you only use 90%, so you can recover that, remove that, becomes normal, or you redo the NMO, become flat one. Okay, so if we compare this to this, you can see events, multiples removed, but if we compare this to this, you can see after multiple removal, your reflections actually appear clear. Well, it's not stronger, of course not stronger, but apparently stronger because of AGC effect, okay? AGC effect. AGC means in the same time window, total energy same. But here, why is in the total energy same, but because in this same time window, you have multiples there, right? So it looks like this energy stronger than this is not true because it's the AGC effect. Based on this display, you can see they actually use AGC, use the AGC. AGC means automatic gain control. That's only for the, I need to emphasize this point here. AGC, most likely you apply only to the data for the display. But the data you store in your storage, you do not apply AGC there, okay? You just keep original data there. So only for the display purposes. So that means you didn't really destroy your data by AGC, okay? AGC, you do not apply the data, only for the display purposes. So every time, well, AGC is very fast. So every time you want to display, use different AGC parameters, fine. Your data is so-called the true data, true amplitude, right? But so-called true means your AGC here display didn't destroy that amplitude. That's it. Right. Let's see the detail about 90% NMO velocity. That's the data we showed before. You have an after the correction, you overcorrected the parameters, and in the FK domain. In the FK domain, this is vertical axis frequency, horizontal axis from -50 to +50 wave number. Yes. In this case, this bit, they call it multiple. Multiple, they think multiple is negative. But well, actually, multiple can be positive, just depending on how define X here, all right? So this side is multiple, so you should get rid of all these multiples. Where's priming? Because this one, if it's completely flat, if any of this is completely flat, that means dipping angle is 0, right? Dipping angle 0 means your energy will be concentrated around K equal to 0. But you have slightly non-zero, so that's energy actually next to K equal to 0. So the energy is here. That's the promise. So what is this here? That's actually nothing to do with the promise. So Edison energy, okay? So that's in the FK domain. After you remove the multiple, after remove the multiple, you only keep the primary here, and the positive side, you end up this one, right? And you have a question or not? No, okay. Well, you were asking me why you still have energy here. This actually is after you do the FK filter, you do the FK transform based on this result generally. So this is not completely 0, right? You have something here. Tapering factor, and also have other facts in the data processing. I just note here, small note here, and in this case, I just put the multiple on the left. Just depends on your software. Some software they prefer keep it positive, and some actually put a negative. This angle is really positive or negative. It's a relative angle, either positive or negative. Now let's see how this demultiple works on the final result. That's a stack section, the real data, field data stack section. That's the water bottom here. Top here is not time 0, okay? Here, time 1 here, 1 second here. So in the left-hand side, the water depth in terms of travel time is 1.5 second. So if for 0 offset after stacking, this should be like 0 offset, okay? That should be, multiple should be like 3 seconds here. So this trend here, this trend actually is water bottom multiple. This is water bottom, this is water bottom multiple, right? Here is slightly complicated, but you can just do the simple calculation. For example, at this point, your water bottom almost 0.8 second, slightly higher than 0.8 second, right? So the multiple will be like a 1.5 or 1.6. So multiple will be 1.5, 1.6 will be here, something here, okay? So in fact, the dipping, I think, very pretty much look like this, and here. And this another multiple, high order multiple. Okay, let's see if we use FK demultiple. That bit becomes much clearer. Here, gone. Just still here is not so good. I tell you the reason. Let's do the comparison. Forward. Okay. But it's not so good. Why? Because we assume water bottom is absolutely flat. Yeah, but it's not. Okay, it's not. So this it's not absolutely flat. So we do need extra tools, other tools to improve that. Improve this one. Now, for the application of FK filter to do the multiple attenuation, there's a number of issues we shall consider. One, as we show on the stack section, in the FK domain, it's not necessarily, the multiples and the parameters not necessarily be completely separate. Depends on the complexity of your data, complexity of a subsurface structure. In that case, I show that if you have the water layer, water bottom is not complete, not deep enough, not flat. You have a stiff dipping. Your multiples is not easy to separate. Okay, so pore separation of a multiple and a primary. That's the one thing, right? Because of dipping event, so in the near offset bit, typically have trouble. So after stack, and then residual for multiple demand is caused by the near offset trace, because you sum everything towards 0 offset, right? That's what we do. For using two-dimensional Fourier transform, F and K, frequency easy, temporal frequency easy, because you usually sample in time in a constant interval. But for the horizontal, for the spatial access, for marine data, seems okay. because you have a stream have a constant interval. Okay, but even for marine, actually, it's not always constant because in the central stream, immediately behind your air gun, that's the constant. But if the side streams, you have angle, right? So even in the stream, the distance are constant, but from the short point of view, the offset, short of receive offset is not constant interval. You see that? Okay, typically for the near offset traces. So, and what do you do before you do the FK transform? You need somehow to uniform your traces. Okay, regularize your traces. Let's say it that way. Regularize your traces so that you have a constant interval. Otherwise, you cannot do the fast Fourier transform, right? If we do, okay, if you say, okay, I honor that the inconstant, the true offset, the variable offset, that means you use a DFT, which is a discrete Fourier transform. That will be really time consuming. Right? So what do? You need to regularize your traces so that you can use the fast Fourier transform for K transform, for the spatial Fourier transform, okay? Time usually okay. Frequency, wave number, the spatial direction usually difficult. Just why we need to do some pre-processing, okay? One more thing, because in the field, usually short interval is larger than the group interval, larger than the trace interval, right? So that's also cause, because CMP, on the CMP gather, on the CMP point, really depends on the CMP interval, really depends on the how many, depends on the ratio of a short interval and the receive interval, right? Remember the formula? Okay, so that means most likely you need to do the short interpolation, right? So that's at least you make a short interval equal to the group interval. All right. So you need to double your data. In the field, maybe you only have every 50 meter a shot, every 25 meter a receiver, but you need to artificially generate a second shot, every second shot, right? So you have effectively 25 meter shot interval, 25 receiver interval. So everything regularized, and then you can do that. You can explore the fast Fourier transform, right? So that's the issue. So you can see here, that's the last one is related to the Ellison problem. Right? If we double the interval, that means your next frequency will be halved. So you are easily to get the Ellison issue. The last one is the Ellison issue. The second one is from a practical point of view, from field acquisition. Your data is not regularized. For lens seismic, definitely it's not regularized, right? Because that line may be not straight even. You have a zigzag, form. Your line need somehow correct to a single line, to the straight line, but also the interval should regularize it. Okay. The second one is from acquisition. The last one is from point of view of Ellison issue. The second one is from acquisition issue. Acquisition point of view. The first one is, because of first one is came from the issues came from the subsurface structure. Okay. Ideal situation, you have a wonderful FK domain transform, wonderful FK domain filter. You can do everything, but in reality, maybe not, because of the dipping angle or complicated subsurface structure. Right, so this the issues related to three aspects. Okay, let's summarize what we learned today. If we have 1 minute or 2 minutes, review, just say, okay, what I'm learning today. This is my summary here. Summary is first one, we're talking about FK transform. Basically, we apply one-dimensional Fourier transform twice. One in the frequency axis, another one follows do the Fourier transform with respect to the spatial axis. Okay, so basically twice. So you transfer the data in the time x domain to the frequency wavelength domain. So just straightforward to FK. Okay. Why we do that? Because in the FK domain, different events can be separated by the dip or inverse velocity. Dip or inverse velocity. Okay. The problem with this, very important problem, is aliasing issue. In the FK domain, aliasing issue appear as a wraparound from the end of next wave number to another side, called wraparound. And the aliasing issue, I just try to emphasize, this aliasing issue not only depends on the delta x, the spatial sampling interval, but also depends on the highest frequency in your data. Remember the formula K equal to F multiplied by a dipping angle. Yeah? So it depends on not only delta K, but also F. Not many people can notice that, but actually you can see the trend here. You see that, okay? Right. So if you, in the ideal situation, you have a proper FK domain representation of a linear events, you can apply a filter in the FK domain. Filter in the FK domain easy, so multiply by 1 or 0 plus tapping off, right? One of the purpose here I showed for FK, T multiple removal. The trick here, instead of we do the proper NMO, use a proper NMO velocity, but we try to overcorrect the priming. Meanwhile, keep the multiples undercorrected. So that means after FK transform, primary and the multiple will be in positive and the negative domain. So they're separated. Right? Finally, I just emphasize for practical data processing or even the acquisition side, you need to consider 3 issues related to the acquisition, related to the aliasing, and related to complexity of subsurface. Right? That's the 3 issues.